Hello everyone. Today I start the topic of counting, which is a very nice and beautiful subject, and it is very useful in computer science, computer engineering, theoretical computer science, and different areas of mathematics. By counting, we mean finding or somehow calculating the number of objects among a set of objects that have a certain property. It will be clear what we mean by counting during the lecture, and to do the counting we have some very simple rules that we should apply in very different situations. I will start by explaining the simpler of those rules, which is called the sum rule. The sum rule says that if some and one object have property P, or in two objects have some property P, the same property P, and we know that these N1 objects are different than the N2 objects, then we have N1 plus N2 objects with property P. This is totally trivial thing, right? And it says that if you could count that some objects have the property that you want, and those number of objects is N1, and in another way you could count that N2 objects have the same property, and you know that these two sets of objects are different from each other such that there is no object in both of these sets, then you have in total N1 plus N2 objects with the property that you want. Actually, this rule is so trivial, it's hard to explain and hard to come up with examples. And let's take the following. How many single digits numbers exist? So we have just one digit, so let's say this is our number, and we can put inside it any one of 0, 1, 2 up to 9, and any one of these gives us a different number, and we get a different number. So here the one single digit number is the object that we want to count. Each one of these digits gives us a different object, which is a set of just single object, and in total we have 10, with the sum of the possibilities, the sum of these, each one of these give 1, and therefore the sum of our total possibilities for a single digit number is 10. As another example, let's take the following. Here is another example. How many students are in the class if there are n students of computer engineering and m students of other majors? Again, the things that we want to count are the students, and we know that there are n students which are computer engineering, but they aren't students, and m students of other majors, but they are students, but these are different from each other because these majors of these m students are not computer engineering. So these are two disjoint sets of students, and therefore the total number of students in the class will be obviously m plus n. So therefore this is the sum rule is a very intuitive rule that even you don't need to think about it, and you will find it yourself and you will use it. Let's now go to the next rule, which is called the product rule, which is much more useful, and in combination with the sum rule allows us to count very almost all of the, a big portion of the counting problems can be solved just by these two rules. Alright, so let's see next the product rule. Here is a way of explaining the product rule. Let us have n objects of type A, and let us have m objects of type B. Then we have n times m and n ordered pairs of objects of type AB. This rule counts the number of ways you can put things next to each other. I have explained it using the notion of ordered pair, if you remember, and if we want to count how many ordered pairs of objects there are, if A has m possibilities, B has n possibilities, then obviously there are mn ordered pairs. This is called the product rule, which you should be very familiar with, and you should see it instantly that this number is correct. I will now explain this by a very nice example. Imagine we have m left shoes, so here this is a left shoe, and m right shoes. And most often you know that left shoes are different than right shoes. And then how many pair of shoes do we have? We have n times m pairs of shoes. That means we can put on an m pairs of shoes, different pairs of shoes each time we go up. Alright. We will go now through a series of examples of counting problems, and we see how by applying these very simple rules we can count many interesting objects. Before I go into more examples, I want to note that the product rule corresponds to the AND word. So when we have n objects of type A and m objects of type B, whereas the sum rule corresponds to the OR word when we have n1 objects or n2 objects of the same type where they are different objects, then we have n1 plus n2 objects. In our next example, let us count the number of two-digit numbers. The question asks how many two-digit numbers are there. The objects now that we want to count are two-digit numbers among all possible numbers. Now I will draw the positions of the digits like this, and here is the first position, first digit, and this here is the second digit. Of course, I mean from the left to right. Let's first consider this position here. How many possibilities we have for this? Now you should think of this of different types of object and how many digits we can put here. We can put all the digits from 0 to 9 in this for the second digit, because for any of those digits from 0 to 9 there is some two-digit number where they appear in the second place. Alright, so therefore we have 10 possibilities for this digit. But for the first digit, we cannot put 0 in the first digit, because if we put the 0 here, it will give us a single digit number. But other than 0, we can put all other digits in the first position. And therefore, for this types of objects here, we have 9 possibilities. And in total, by the product rule, the total digits are pairs of digits of the first position and the second position. Then we have 9 times 10, which is 19 two-digit numbers. And to check that our answer is actually correct, we can solve this problem in another way and saying that from the numbers, I write it just here, 1 through 99, there are 99 numbers. There are exactly 9 numbers which are single digits, and those are 1 through 9. And then the total number of two-digit numbers are 99 minus 9, which is 19. Therefore, our way of counting is actually correct. We were sure before that, but we also checked it here, like this. Let's see now another example. The example asks how many binary strings of length n are there. Recall that a string with any set of alphabet consists of just putting the letters of alphabet after each other, and the length of that is the number of letters that you put one after each other. And here when we say binary string, we mean that our alphabet consists of the digits of or symbols 0 and 1. And therefore binary strings of length 3, for example, are all the possible ways that you can put 0 and 1 in 3 positions, like this: 1 1 0. And it is actually quite obvious that all of because of the binary number that they represent, how many are there. But I want now to count the total number of strings of length n in a way that is very helpful for us in other problems also. Therefore, let me go count like following. I will draw the string like the following. Again, I number the positions of the string because we have n letters, we have n positions. So I say this is the position 1, position 2, position 3, and position n minus 1. Again, I repeat what we did in the previous example. In any one of these positions, we have two possibilities. Either a 0 will appear here in any one of these things, or a 1 will appear. And these are objects of different types because they are totally unrelated to each other, and by repeating the product rule for 2 positions, then for 3 positions, and then for m positions, we find that the total possibilities for all the strings, for all the ways to have objects of the type which consists of the ordered pairs, the ordered n tuple of the types of these single cells, if I want to use that terminology, is just 2 times 2 times 2 times 2 times 2, and this will be in total 2 to the n. Again, each cell here, each position, has two possibilities. It can be either 0 or 1. And if we fix any one of these possibilities for any one of these cells, it will give us one binary string. And because we have freedom to choose in each cell between 2, the total number will be 2 to the n. So this is a repeated application of the product rule, which should be clear to you. Another way of counting these numbers are by saying that any string here, by counting the number of 0, 1 strings, is by saying that any string here represents a binary number, if you remember, numbers which are written in base 2. And when we have n digits, we can represent numbers between 0 and 2 to the n minus 1, which are exactly 2 to the n distinct numbers. That was another proof. But the way we now want to count is by applying the product rule and saying that each cell has 2 possibilities, and these are independent from each other, and the ordered types of objects that we get, the ordered tuples of different objects that we get are 2 to the n many. Our next example asks, in our next example, I want to give a different proof of the fact that a set of n elements has 2 to the n subsets. You recall that we did a proof by mathematical induction, which was not very simple, perhaps a little bit non-trivial, but I want to give here a proof using the counting rules, which is much simpler. Let me take for this set that we want to count its elements, some set S, and let us represent its elements by S1 through Sn. Then I again draw these different positions, and I order so you see already that I have ordered the elements of S by this subscript, so I say that this is the first, second, and like nth, and now I put these associate each one of the elements to one of these cells, and it's not important in which order, but I just say that this is the cell of S1, this is the cell of S2, this is the set of S3, and here this is the set of Sn, and this is the cell of Sn minus 1. Now I just want to observe that we have the following transformation between the strings, binary strings of length n and subsets of S, and in a way that each binary string will correspond exactly to one subset of S, and one subset of S will correspond exactly to one binary string. And let me explain how to get a subset out of a binary string. So let me write it here. So let W1 through Wn be a given binary string. Define a set S sub W by the following rule. Si is in SW if and only if Wi is 1. Let me take an example. Let us have only 3 elements, and I take a W which is 1, 0, 1, and I think that the digits of W, the 0, 1 numbers, are in these cells, and then I take the subset which has the digit 1. So in this case, S of W will be the subset S1 and S3. And we can extend it by saying that everywhere else like is 0, and then we can think of it as actually a subset of S. Now it's quite clear that this operation gives a 1-1 correspondence between these two sets, and therefore they have the total number of subsets of S is the same as the total number of binary strings of length n, which is 2 to the n. The next example asks the following. Count the total number of functions f from a set A with m elements to a set B with n elements. So the problem asks, find all the possible all possible functions that go from a set A into a set B, where the cardinality of A, or the number of elements in it, is finite and is M, and the cardinality of B is finite and is M. Now it seems at first a little hard, but it's actually quite exactly the same as we did in the previous examples. I will again draw my positions, and this time I think of these as showing my function or defining my function. So let me first write A as A1 through AN, and I want to write out my function like the following. I write f of A1 into the first cell, f of A2 into the second cell, I write f of A2 in the second set all the way, and f of AN in here. Now it's obvious that any function that is possible, it can be written in this way by putting in these cells its value, right? I put the value here for the function f. So let's now see how many possibilities are there. B has n elements, and so any function f can map A1 to any one of the n elements of B. Well, there's no restriction on it, so there are n possibilities here. So in this cell has n possibilities. Again, assume the function we are counting has mapped already A1 to somewhere, and we want to know where it wants to map A2. But A2 also can be mapped to any one of the elements, or it can be sent by F to any one of the elements of B. And therefore that one also has n possibilities. Alright, so the second cell has n possibilities, then any one of these cells has actually n possibilities. Correct? Because again, any function can map A1 to any place, A2 to any place inside B, so it can assign any value to A1, any value to A2, and to AI, again, any value. And a function therefore corresponds to a choice between all the possibilities for f of A1, all the possibilities for f of A2, and all the possibilities for f of AN. And the unique function is given when you fix each of these choices, which corresponds to a tuple of these different types of objects. And then therefore the total number of possibilities for a function is n times n, so each n, one n for one cell above, and therefore this will be n to the n. Thus n to the m is the total number of possible functions from a set of m elements to a set of n elements. The final example of today's lecture is the following. Count the number of one-to-one functions from A to B, where again A has m elements and B has n elements. So now this time we don't want to count all the functions, but we want to count only one-to-one functions. I again write my cells as before, and remember that these represent the possibilities for f of a1, f of a2, all the way to f of an. Now, a function which is one-to-one, remember that it can map at most one element of A to any element of B. Okay, so let's see how many possibilities the first element of A has. So the first element of A has no restriction. So let's now A1 be just the first element of A, as we have ordered it. So the first element has no restriction, and therefore it has n possibilities. I write under the cell the number of possibilities. But now, what is the number of possibilities for the second element? The second element, for the second cell, now the second cell cannot be any value, or the second element of A cannot be mapped to any element of B because it is restricted. Now the function has to be one-to-one, and the second element cannot be mapped to where the first element was mapped to. Therefore, it has one less possibilities, and it has n-1 possibilities. In some typical cell here, the case cell, f of ak can be any member of B other than those we have already been covered by the images of the first k-1 elements of A by that particular function. Therefore, the total possibilities for sending a k to somewhere for any function is n minus k minus 1, because any function has already sent a1 through a k minus 1 to somewhere, and it cannot send a k to those elements which are already image of something. And therefore, any function has n minus k minus 1 possibilities or choices for its ak, for the ak. And we continue like this, and n has n minus m, here is m, plus 1 possibilities, which is n minus m minus 1. Here also should be n minus k. And again, by the product rule, we get that the total number of one-to-one functions f from a to b is n times n minus 1 times n minus 2 times n minus n plus 1. Now, this is, you see, a little intuitive, and to give a very rigorous and totally convincing proof that the way we counted the total number of one-to-one function is correct is by saying that I have these choices, and which corresponds to a set of, let's say, ordered m tuples, and I have all of my functions which are one-to-one, and any one-to-one function can be mapped to one possibility that I counted in a unique way, and each possibility that I counted gives me a one-to-one function in a unique way. And when we prove that, we have formally, or we have rigorously proved that we have counted correctly. But as long as we want to count objects and it is intuitive that what we're doing is correct, we don't need to actually prove in a rigorous way that our counting is correct. And here it's actually quite simple to see that any functions put just some values in here, and it gives us a set of tuples which their numbers among those things that we have counted, because each function gives us some values in here of b, and which has a special structure where these are distinct. And now if we want to count how many distinct m tuples of elements of B exist, this is their number, and the set of distinct m tuples of B are in one-one correspondence with the set of all the one-to-one functions. By a distinct m tuple, I meant m tuples where there is no repetition among their entries.